Hello everyone, I am Srinidhi Hegde from TCS Innovation Labs, and today I will be presenting our work on Variational Student, which is an efficient framework to learn compact and sparser student networks in knowledge distillation framework.
Deep neural networks are computationally expensive and memory intensive, making them unsuitable for real-time applications. Miniaturization of devices such as smartphones, drones, head mounts pose constraints on computation, memory, and battery life, making it harder to deploy deep neural networks in such devices. Furthermore, neural network compression ensures data privacy in applications which use neural networks to process data for the edge devices by removing the need of on-cloud processing. Neural network compression has direct impact on many application domains such as augmented reality, robotics, healthcare, and unmanned aerial vehicles. Now let's have a look at some of the common procedures to compress neural networks. Pruning and quantization are the most common compression techniques in literature. Pruning involves removal of redundant parameters or connections between the neurons in the neural network, which are not sensitive to the performance. Network quantization techniques compress the original network by reducing the number of bits required to represent each weight. Low-rank factorization involves converting the neural network weight tensors into low-dimensional representation for efficient storage. Sparsity constraints in training create zeros in the weight tensor, inducing an effect similar to pruning. For convolutional neural networks, since convolution dominates the overall computation, many recent works design efficient convolutional filters for achieving significant speedups and memory footprint reduction. Knowledge distillation involves transferring relevant information from a complex, deeper teacher network to a simpler, shallower student network. During inference, we obtain a compressed network consisting of fewer parameters. Our proposed method is primarily based on sparsity constraints and knowledge distillation. Other compression techniques could complement our proposed method to enhance compression. In our work, we aim to create a compact and a sparse student network from a given teacher network with a minimal compromise in accuracy. Specifically, we use variational dropouts for inducing sparsity in the student network in the knowledge distillation framework. Overall, the knowledge distillation provides compactness through student architecture selection and aids training using the knowledge extracted from teacher. Variational dropouts, on the other hand, allows flexible sparsification of neural networks in a nice learning framework. We call this combined approach as the variational student. Before proceeding further, let's see how we train a student network in the knowledge distillation framework. Consider a dataset D with inputs and corresponding labels pair X and Y respectively. As we see in the figure, the teacher network is a deeper pre-trained model and the student network is to be trained with the dataset D. We use the loss function LKD shown on the slide to train the student network. The loss function consists of a task-specific loss for student, which in our case is a cross-entropy loss for a classification task. The second term of the equation represents the hint from the teacher. This term forces the student to mimic the teacher network by minimizing the KL divergence between the softmax outputs of student and teacher networks, which are ZS and ZT respectively. Also note that in this framework, only the student network is trained as the teacher network parameters are not updated during the backpropagation. The training procedure for learning compact and sparse student is similar to the knowledge distillation training. The difference lies in the introduction of additional terms in the loss function, which are variational term and the block sparse regularization. Note that we also introduce a new variational dropout parameter alpha, which is optimized by variational term to promote sparsity. Now I would like to talk about the variational term used in the loss function. To understand the variational term, let's look at the Bayesian inference. Bayesian inference involves computing posterior distribution using the Bayes rule. This usually involves computation of intractable multidimensional integrals, so we need to use approximation techniques. Variational inference is one such approximation technique which approximates the posterior distribution P by a parametric distribution Q parameterized by phi. The quality of this approximation is measured in terms of KL divergence. The optimal value of variational parameters phi can be found by maximization of a variational lower bound shown in equation 1. This bound is known as evidence lower bound or elbow. Variational term used in the training of the student network represents the KL divergence term in the elbow to model the posterior distribution of neural network weights. We analyze two variants of the variational term based on the selection of prior distribution. The first variant is an approximation of the KL divergence term derived from the sparse variational dropouts or SVD as shown in equation 3. This assumes a log normal prior on the model parameter distribution. Equation 4 shows the second variant, which is an approximation of the KL divergence term derived from the variational Bayes dropout or VBD. This term is obtained when we assume a hierarchical prior on the weight distribution. The last term of the loss function is the block-sparse regularization term, which helps in promoting sparsity. The block-sparse regularization, or BSR, is a popular technique used in some of the well-known traditional multitask learning approaches. BSR is shown to promote sparsity in the multitasking model parameters when the tasks are similar. Extending this idea to our case, we apply BSR on an aggregated tensor of the teacher and student weights. Since the tasks performed by teacher and the student models are the same, we expect that this constraint promotes sparsity in the aggregated tensor and hence in the student weight tensor. The BSR is mathematically defined as the L1 by LQ norm. Let us look at an example to understand this operation. Assuming the teacher and the students to be a multi-layer perceptron, we model the weights as 3D tensor. Let the concatenated weight tensor be WT:(S). BSR first reduces the weight tensor to a vector by applying LQ norm along the dimension L and M. Then we compute L1 norm of this reduced vector to get a scalar value as the output. In our analysis, we used both L1 by L2 or group lasso and L1 by L infinity norms. Effectively, we can also see that the non-Bayesian nature of the variational student provides us greater flexibility in incorporating constraints such as BSR that may help in sparsity gains. We perform experiments and evaluation for primarily two classes of neural networks, which are multi-layer perceptrons and convolutional neural networks. For MLPs, we use a two-layered fully connected network with 1200 nodes as the teacher. For the student network, we use a two-layered fully connected network with 550 layers and a LayNet 300-100 model. We train MLPs on MNIST dataset. For CNNs, we use VGG90 as the teacher network and LayNet 5 Café as the student network. Both of these networks are trained on CFAR10 dataset. We use 4 evaluation criteria to evaluate our work, which are compression ratio, which is defined as the ratio of the total number of weights and non-zero weights of the neural network; per layer sparsity, which is the percentage of zero weights in each layer of the network; memory footprint is the space occupied by the model in the memory; And finally, top 1 accuracy in class predictions. Let us now look at some of the interesting results of our work. The figure depicts the weight distribution in two different layers of teacher network and student network trained in different scenarios. We see that knowledge distillation framework is unable to create sparsity in the student network weights. When the training is performed with variational dropouts, there is a quantum leap in sparsity of the student network weights, which could be inferred from a large number of weights concentrated around zero. Furthermore, the VBD variant performs marginally better than the SVD variant in promoting sparsity. This is represented by a taller peak in the VBD graph. We also analyzed the sparsity induced by BSR on student weight distributions. The figure shows the weight distribution in two different layers of student network when BSR is applied on a composite tensor consisting of weights from both student and teacher networks, and when BSR is applied only on students' weights. We see a sharper peak indicating more zeros on taking teacher network's weight into consideration, indicating teachers' role in inducing sparsity in student network. We compare our technique against both Bayesian and non-Bayesian state-of-the-art network compression techniques in the literature. The comparison is performed on a LayNet model as student that is trained on MNIST dataset. We report that the hierarchical prior used in the VBD variant improves accuracy and sparsity over Bayesian techniques such as Bayesian doc knowledge or BDK and Bayesian compression or BC, which uses half-Cauchy prior in modeling the network parameters. Note that although iterative pruning or IP has lower error rates, it does not achieve sparsity. Our method provides competitive accuracy when compared to such methods. Thus, we demonstrate that our proposed technique strikes the right balance with respect to the trade-off between compression and performance of a model. Deep neural networks have extensive dependence on large amounts of training data. It becomes difficult for neural networks to perform in low data paradigm, which is typically the case in active learning and reinforcement learning domains. Variational student framework could be deployed in such domains as it performs significantly better than state-of-the-art methods in low data scenarios as seen in the figure. This behavior could be attributed to the hint from the teacher network, which acts as a proxy for input data, leading to better accuracy. To summarize our results, we achieved a compression of up to 64 times for MLPs and 213 times for CNNs, which means that the memory footprint reduced from 9.3 MBs to 147 KB for MLPs and 532 MBs to 2.5 MB for CNNs. We observed a drop in accuracy of only 0.08% for MLPs and 8.7% for CNNs. On an average, a fully trained student layer reported a per-layer sparsity of 95.27%. The student network takes around 0.46 milliseconds for inference, which equates to a speedup of 37 times over the student's inference. This is credited to the lower computation in the student network. In conclusion, we see that the variational student framework produces a sparse and a compact neural network with a minimal compromise in accuracy. The variational student framework provides a greater flexibility in combining Bayesian sparsity-inducing techniques such as variational dropouts with non-Bayesian constraints such as BSR within the knowledge distillation framework. Furthermore, we achieve a compression of up to 64 times and 213 times for MLPs and CNNs respectively. The variational student framework is shown to perform significantly better than the state-of-the-art methods in low data scenarios. A student network trained using the proposed framework performs inference in real time.
For further questions and discussions related to the work, please reach out to shri.hegde@tcs.com. Thank you very much for your attention.